This is the English re-recording of a keynote I gave at this year's WJAX conference in Munich. It was in November 2023, and I want to talk about empowerment of subject matter experts, why you should completely isolate subject matter from technical concerns, and how. So, if you don't recognize this, these are the various tools that can be used by, in this case, a computer-controlled mill, right? A machine that removes material from a workpiece in order to, whatever, manufacture something. And the user of such a machine, some work person in a metal manufacturing company, something like that, if they want the machine to manufacture their part, what they do is they express the requirements they want. Maybe they create a sketch or describe it in text. They explain that in text, and then they send these requirements to the manufacturer of the CNC machine. And then what they do, they send back an updated firmware, usually 4 to 6 weeks later. And with this updated firmware, you can flash this onto the machine, and now you can manufacture your part. If this sounds crazy, that's because it is, right? That's not how it happens. Of course, these machines are user programmable, and so you, as a user of the machine, you directly, program the machine to do whatever you need, or your CAD program sends down, the coordinates that need to be milled. Here's another example. This is the ALMA, or a couple of antennas from the ALMA telescope array. It's a 64, I think, or maybe originally it was 64. Well, it says 63 there, so probably number from 0 to 63. So, computer science. 64 antennas in the Chilean Atacama Desert, and if astronomers need the telescope array to observe something in the sky, for their science, then what they do is they describe what they need observed, and then, software developers, you get the point, right? Of course they don't, because these kinds of observatories are user programmable. Again, like the CNC mills, you can even remotely operate these things. You can sit at your university and, instruct the telescope what to do. Unfortunately, because you can't travel to these cool sites, although I guess once you've done it enough times, you probably don't want to. Anyway, these machines are user programmable. So how this works is there is some kind of software system, and the subject matter expert, the mill operator or the astronomer, they want to control that machine, or they want to control the software machine, that as the software system that then controls the machine. And they do that by creating, modifying, testing, and ultimately executing some kind of model program configuration that describes what they want the machine to do. More specifically, they use a language that has been built for this particular purpose, and that is used to create, modify, test, run these models or programs or configurations. And this language covers the domain of CNC manufacturing or radio astronomy. And the language is built together by software people. They also build a software system. They understand and abstract the domain to build a consistent language. They usually do this together with a bunch of domain experts, right? Really experienced astronomers or something, collaboratively, iteratively, who deeply understand the domain. And of course, there's a feedback cycle from the actual users of that language, practical experience on how well the language works. What we want to optimize, therefore, is this path from the subject matter's requirements, or even, if you will, brain, into a running software system. That's the path we want to optimize to make this faster, more efficient. Now, something completely different. There are other systems where the subject matter expert writes requirements, or, call them user stories or epics or whatever. Maybe they don't write them, maybe just they explain them to the software people. But in any case, there's this indirection through informal, non-executable, misunderstandable, imprecise prose. You can get it precise, but it's a lot of work that hardly anybody bothers. So the software person then perhaps misunderstands what the requirements mean. It's not that uncommon. and creates a software system that doesn't quite do what the subject matter expert wants, and actually usually does take the 4 weeks at least that I was joking about at the beginning in terms of the CNC mill. Of course, again, the subject matter expert does this based on the domain understanding, and then of course they try out and validate the software system. And of course it's not, I mean, maybe that was the case 30 years ago, that the requirements were written and then, as they say, thrown over the proverbial fence. But of course this is done collaboratively, iteratively as well. But again, there is this indirection, the written informal requirements. And we see that in a lot of systems, right? In insurance products, telecom pricing models, tax calculations, salary calculations, tachograph rules, clinical drug trials, digital therapeutics, and all kinds of other things. And so, yeah, why, is this inefficient indirection through the requirements going on? So just to drive this home, for example, if we go to the tax case example, like every little change of the requirements of the actual tax law, like, I don't know, some kind of tax rate changing or some condition when the tax is applicable and when it is not, every little detail has to be programmed by the software people after they have gotten the requirements. Sorry. This is, of course, much more annoying, honestly, to the software people and inefficient than just once building a language that has things like currencies, dates, percentages, arithmetic operations, data lookup tables, versioning, testing, and stuff, and then give that language suitably designed to the subject matter experts to program directly. So again, why? Why don't we let the experts program? Put that in quotes because some people don't like the term. They prefer configure or model or specify, whatever. Doesn't matter. So why don't we let the experts program the subject matter directly? So again, in the case of the CNC machines or the radio telescopes or let's say game engines, this programmability is essential to the system. There's no point in having a CNC machine that isn't programmable. Same for radio telescopes or game engines. But in the other examples I gave before, the programmability is seen as optional. You can use the traditional approach through the pros. It's inside the same company. People talk to each other anyway. They don't want to be programmers. They don't want to whatever, right? So, possible. But should you use this approach? Shouldn't you rather do the programmability also for these systems that we were talking about here, these systems where it's not an essential property of the system, but perhaps, maybe, probably still a good idea. So my goal in this talk is to convince you to consider the approach of programmability in more systems than, what is done today. So when should you use the approach? Well, first of all, there needs to be sufficiently complex and large subject matter in the domain. Right? There's no point in doing this for some trivial stuff. Like the counter example I always like to give is if you implement a shopping basket, shopping cart, sorry, for your web shop, then sure, there's a lot of non-functional requirements, scalability, performance, blah, blah, blah. Don't want to make that sound trivial, but the actual subject matter, the business logic of a shopping cart isn't that complicated. So separation probably makes no sense. In tax law, it's really different. The tax law itself is so complicated. There are specific experts on the topic in your organization typically. Same is true for example, clinical trials. So another reason when you should do this is if that there is sufficient variability in the domain. So there is, there's space for configuration programming or change over time, right? Again, the ALMA telescopes will probably run for, I guess, 20 to 30 years. And lots and lots and lots of different observations will have to be done, and somebody has to, quote, program them, right? Another reason why you would want to use the approach is that there are many different instances, right? So again, your CNC machine, if you're a, slightly advanced machining shop, you manufacture different stuff like every other day or every few days, right? So you have to, there's there's a big need for programmability. There's really no point in sending the requirements to the manufacturer of the machine. And again, the domain needs to be long-lived because obviously building these programmability configuration languages and tools is a bit of work. It pays off only if the domain is reasonably long-lived. But again, in the examples that I tend to repeat here, that's the case. You know, a company that does tax to calculation products doesn't switch over to some random other thing the next day, right? So they do this for years, maybe decades. Same is true for essentially all the other examples. So why is this approach a good idea? Why should you use it? First of all, the subject matter experts are empowered, right? They're no longer second class behind devs who, quote, just write the requirements and then hope that the gods in front of the computer are able to, you know, correctly implement it and hopefully even quickly and, you know, blah, blah, blah. It's much better if they can do it themselves. The developers, in contrast, can focus on technical concerns, right? They don't have to understand and be bothered with every little change in the subject matter. There's this separation between subject matter and technical stuff that has architectural benefits. I'll get to those, but also the people, you know, the experts in both fields can do what they do best. The subject matter is portable, right? The legacy problem is much reduced. If you need to run the same subject matter on a different platform, implemented in a different programming language, it's reasonably easy to do. You just run your configurations on a different runtime engine. You have to build that, of course, but the subject matter itself, all the work that the subject matter experts put into the system is still valid and needs no change, most likely. The collaboration between subject matter experts and the developers is better. Now, again, this is maybe a bit unintuitive because this whole story here sounds like I'm trying to separate technical and subject matter people, you know, which is a bit counter to a lot of, you know, agile and, you know, soft skill, you know, how does collaboration work experience or, you know, in the last couple of years and decades. That's not what's happening. Because they have this language as the, if you will, formally defined contract between what the system does and or can do and how it's done, technical stuff, this collaboration becomes better. I've seen this over and over again. Oops, sorry. And overall, the subject matter development process becomes faster and more agile, right? Obviously, I wouldn't propose anything that doesn't make stuff faster, better, cheaper, and so on. And there's this other thing that in Germany, at least, probably in Europe, we talk about a lot, which is the Fachkräftemangel, meaning that there aren't a lot of experts in anything, right? You can't find anybody to hire. So, and there's also this general notion that we have to improve our competitiveness, you know, to, you know, what they say usually is to fight against China. So we have to do something, right? I mean, there's lots of things organizations can do, like reduce a lot of bullshit and crappy processes, but, you know, these kinds of architectures help as well. Again, there are trade-offs. There's no free lunch, not even here. You have to understand the domain very well to build these configuration languages and tools. Could argue you should do this anyway. You know, DDD also proposes that or emphasizes that quite a bit. You have to build and evolve the language and the tooling, which only pays off if you use it a couple of times, you know, getting back to my when discussion a few moments ago. And there is a training need and a culture shift for subject matter experts. They aren't used to working like this, and it's a big change. And as you all know, big change requires, you know, explicit management and care and dedicatedness, and, you know, it's something that needs to be consciously designed and implemented. It doesn't just happen if you give people a tool, right? There's different responsibility now because the subject matter experts, if they implement their shit wrong, then the system executes wrong. Obviously, there's going to be testing and stuff, but still, they can't, you know, blame the developers that they implemented it wrong. It's now the job of the subject matter experts. So again, culture shift that needs design and care. Now, there is a manifesto we wrote a couple of years ago, the Subject Matter First manifesto, which explains this whole idea, and you can sign it if you agree with it, and then nothing happens, but you can still sign it. You can become part of the community. But let's now move on to the hows, right? How do you know what goes into the language, and how do you build these kinds of systems technically or architecturally? So let's talk about the what goes into the language first. I actually wrote a whole book about this. It's called How to Understand Almost Anything, a practitioner's guide to domain analysis, because this process of understanding a whole domain is called domain analysis. Currently, if you hurry up, maybe 3 more weeks, the book is 50% off. And after that time, it's, I think, $25 or something, so it's reasonably cheap. It's also not a huge book. And this book explains the process, right? And let's briefly define the term domain analysis. It's about understanding the structures, rules, constraints, and behaviors of a domain precisely and completely enough to make it accessible to people and software tools, right? It needs to be formalized, so tools, you can build a tool to program stuff. So again, you understand structures, constraints, rules, semantics, models, and stuff. You understand what I said before in order to build formal data structures, implement constraints, implement interpreters, modeling languages, and stuff like that. And from that, you can then, in the next, if you will, indirection, also derive APIs, software architectures, checkers, compilers, UIs, simulators, transport protocols. I'm not saying this is all automatic, right? But the formal representation of the domain is a great starting point for defining these second-level artifacts. Actually doing this more or less as we speak in a project currently. So again, how do you do the domain analysis in a little bit more detail? There's 3 phases: collecting, thinking about it, and validating it. It's kind of trivial at that level. I'll explain a few more details. And then you iterate, right? Very important. This is not a waterfall. You don't collect for 2 weeks, think for a week, and then validate for a half a year. It's not how this works. Usually I run through these cycles every day. So what does collect mean? It means that you talk to experts, maybe read material, run workshops, and capture what you learn about the domain. You emphasize a consistent terminology, otherwise no conversations work well, right? So that's the first phase, or the first, shouldn't say phase because it's not really sequential, but the first set of activities. In thinking, there's a couple of important things. One is that you actually take your time to really think through things. This is often not happening in many projects I'm part of. Is no real time for deep thinking because everybody's calendars are full of meetings. There's just no time to do any work. You want to consciously remove cruft, right? Old stuff that nobody needs anymore, that makes consistent abstraction complicated or ugly. And you want to specifically address domain crosscuts, things like versioning, I don't know, temporal data, stuff like that. Something that's not even obvious if you think about the domain itself. It's usually really the result of significant understanding. Validation is then the activity of checking that the abstractions, the language you've built, actually works and is able to cover the domain and is also accessible to future users. So you let the users play with a domain implementation. You implement the domain in something that lets you implement very quickly. This is where I like to use domain-specific languages, but you can hack it in Python if you're fast enough, right? That's fine. The point is that if you spend the morning collecting and thinking with your domain expert buddy, then in the afternoon you should be able to implement that stuff so that the next day people can play with it. You really need that kind of speed in that activity. So that's all I want to say about the how do you know what goes into the language, because again, you can always buy the book and read up on it. It's reasonably priced, so you really can get it. So how do you do this technically? So first of all, let's look at how the artifacts and stuff kind of works. So you have this model, right? You start in some kind of configuration tool. I'll call it IDE here. You edit it, right? And then you typically run a structure check in the sense that whatever you create conforms to your language structure, right? You can only express things that your language structure or your configuration model allows you to do. You send it to the target system, and there it's executed. The way I've shown it here, there is no translation involved, so there's basically an interpreter running on the target system that runs your model and does whatever it needs to do in the target system in terms of invoking usually manually implemented behavioral building blocks. Now, sometimes or usually there is some kind of runtime validation happening as the system is interpreted on the target system. Sorry, as the configuration is interpreted on the target system, there's error checking, and if some things go wrong, if something fails, an error is reported back in some way to the person who created the model. Usually there is some static validation going on. So before you ship it to the target system, you do, for example, some kind of static type checking and static consistency checking beyond the pure structure. And often then, I mean, these two aren't necessarily, combined. You can do static validation with downstream interpretation, and you can do compilation without static validation, although that's kind of weird because compiler needs to understand the program. Anyway, you translate your configuration model to some kind of other representation, which you then actually ship to the target system. Some, I don't know, JSON data structure or something, which then is maybe, again, statically and runtime validated on the target. The whole target system, again, has an interpreter or runs the generated code, which then, relies on frameworks, libraries, and stuff that in turn access traditional system components, UIs, databases, APIs, whatever. And there's also often a secondary execution environment that runs in the IDE. It's often an interpreter, and it is used for testing. Because, of course, you want to make sure that your subject matter experts can do test-driven subject matter development, right? They should be able to not just specify what they think the system should do, they should be able to run it and test it, because otherwise they can't take responsibility for what they're specifying. Let's look at another perspective here, and that is how you build these kinds of languages. So there's in these kinds of discussions, you always have these 4 meta levels, which again sometimes people are put off by the term meta and shit like that. Don't be, right? It's just words. But you have these 4 levels where you have this level of a language you define, blue here. Above that you have a language or a tool for defining languages. And once you have the language, your language, the blue one, you can use it to build models. And then there is runtime data, which at this point we don't have to care about. So you can see lots of examples like that, right? There is, for example, JSON or XML or other ML, YAML, whatever systems, which are essentially languages for defining data formats. Data formats are a simplistic version of a language. These are usually called schemas, and then once you have the schema, you can create a document that conforms to the schema. That's a typical process. You can see that also in classical compiler construction, where what you create is the grammar, and you use things like Antler and JavaCC and Lex and Yak and stuff like that to build your language definition, and then you write code or sentences that conform to the grammar on the M1 level. Or if you're more a modeling person, maybe experienced with Eclipse, then Eclipse's EMF, EMOF, MOF kind of is on the M3 level. You define meta models, and then models are, again, the instances your users might create. And last but not least, in the semantic modeling community, you have things like OWL, which you use to define ontologies and stuff like that. And then the instances of those, I think, are called instances. So this schema of this 3, or depending on whether you care about runtime data, 4 level meta hierarchy is very common, right? And so we use that here as well. So how does this look in a little bit more detail? Usually on this M3 level, meaning the tools for defining languages, you have, a language for language definition that consists of, things have properties, things have links to other things, right? Very abstractly. Usually the links are separated into containment and reference, the usual composition, the target dies when I die kind of thing. And often things can inherit from each other. So a thing has a super thing, right? Animal as a kind, no, I should say a dog is a kind of animal. And once you've done that, you can use this language, the the ugly green language here, to define your own one. For example, a geometry might be a thing, a shape is a thing, a geometry has a containment link relative to shape that, the geometry contains shape, and then shape has a couple of specializations, lines, rectangles, and arcs, where line has a start and end point, rectangle has a top left and bottom right point, and arc maybe has a center and radius, right? So this is how this would work. And then if you go, and then, to make it a real language, you have to think about concrete syntax, which could be text, tables, diagrams, UIs, whatever, about validation rules and the runtime semantics. Again, this is obviously needed, otherwise you can't check your models for correctness and or run them, right? You have to define what things mean and when things are correct. So one meta level down, once you have your geometry, shape, language defined, you can now, for example, create a model G, an instance of geometry, and it contains a line L1, right, from 0, 0 to 5, 5, and another line L2, another instance of relationship from 5, 5 to 5, 10, and maybe an arc with a center at 20, 20, right? So this is how you do this, and again, how you express these three levels, whether you do it with XML-ish technologies or language technology or modeling technology or semantic technology, they all have different trade-offs. I'm not saying they're equal, but the general approach is always the same. So talking about tools, I want to point to a couple of them, and I focus on this language and meta modeling environment. I think I don't have a lot of experience with the ontological world, so I'm gonna stay away from that. And I don't think that XML and JSON as such are good enough to do this language work. They are useful in that context for storing shit, but they're not the right mindset and tool set to do these kinds of languages. So I'm gonna stay with these. And the system I work with most is MPS, the Meta Programming System by JetBrains. A great tool for building really sophisticated domain-specific languages. So you might want to check that out. There are, as I mentioned on the colorful slide there is Antler, and then there is a bunch of editor frameworks with which you can build textual editors that run on the web based, for example, on Antler grammars. Actually, CodeMirror has their own grammar definition formalism. So Monaco and CodeMirror are the two there. There is Langium by Typefox, which is a TypeScript-based, browser-based language development environment. It's like Xtext++. I'm no longer mentioning Xtext because it's kind of dead-ish, right? It's no longer actively developed as far as I know. There is Modelix, which is also a large-scale model repository and editing and management and processing framework developed by ATMS as open source software. And then there is LineWeb, which is an open source initiative by some of the people involved in some of the previously mentioned tools, which aims at developing the necessary protocols and interfaces to have, repositories and editors and validators and other building blocks for such an environment, for such a language-based environment to interoperate. So worth checking out. So if you want to roll your own, if you don't want to use any of these tools, what do you have to do? And I actually currently more or less have to do that with colleagues, of course, as usual, where we need all this model infrastructure in C#. And if you go back to the technology, I mentioned there wasn't anything that sounded a lot like .NET, so we have to build this on our own, and we do it basically by reusing a lot from LionWeb. So even if you roll your own in terms of implementing it on your own infrastructure, take a look at the LionWeb stuff, because there's a lot of things you can reuse and you don't have to completely reinvent. But in any case, what you need then on the M3 level is a formalism to define meta models, right? You have to build your thing, property, link infrastructure, data structures to represent models in memory, APIs to read, traverse, and modify these models, formats to persist them, ideally generically, right? You don't want to have to define a serialization or storage syntax for every kind of language. You need a syntax for the user, right? User facing, but you don't want to just to store things. Don't want to do anything. This should be generic, in terms of M3, and probably some kind of rudimentary but generic way of editing them, some kind of tree view kind of thing. The model API then is also a model API is also needed. You have to be able to say I have a node here and I need the children in some kind of child collection. Like if my geometry has a bunch of shapes, I need to get all the shapes in my geometry that I pass in, right? Things like that. And again, the meta model definition, a representation of your language structure in terms of your programming language that you want to use to process the models. On top of that, storage, query, notification services, all kinds of stuff. Many of these things, for example, are available in EMF, which is why traditionally EMF has been used a lot for that. Now, the whole Eclipse stack has certainly lost quite a bit of its mojo, I would say. Web, cloud, blah, blah, blah. It's not Eclipse's home turf. I'm not saying it's bad stuff, certainly not. But anyway, check it out. Maybe check out LionWeb as a very small but useful set of infrastructures for these kinds of systems. So a few closing thoughts and a nice picture of a glider. So something about domain-driven design. Now, domain-driven design, if I steal the definition from Wikipedia, says, among other things, it places the primary focus on the core domain and logic, core domain and domain logic. Agree completely. It bases your design decisions. It bases the designs on a conceptual model of that domain called ubiquitous language. Agree. And you then initiate a creative collaboration between technical people and domain experts to iteratively refine a conceptual model that addresses particular domain problems. Okay, yes, nothing wrong about that. But again, I agree to all of this. But in my opinion, you should go one step further, at least for domains where this programmability is useful. Go back a bunch of slides to the when. Where you reify this conceptual model into an actual configuration programming-ish tool, right? Domain-specific language. And so this then allows your subject matter experts to directly express the subject matter and not just, somehow iteratively, collaboratively with the domain, with the programmers. More Wikipedia. Critics of DDD argue, says Wikipedia, that developers must typically implement a great deal of isolation and encapsulation to maintain the model as a pure and helpful construct. Yes, I agree, but I don't see why this can be seen as critics. I think the separation of the subject matter and technical stuff as, isolated as much as possible. That's great. That's not a drawback, right? At least in many systems. And so I don't think this is a criticism, right? It's great, right? So I think working with domain-specific languages and building these kinds of programmable systems that I'm trying to sell you on here is a bit like DDD++, right? And I'm surprised not more DDDers care. Actually, there's few DDDers who care, and I just don't get that. Another thought. Automation and tools. Now, this is obviously a car production street. It's not called street in English. In German, it's Produktionsstraße. Anyway, the thing that Ford invented, I forget the name. Anyway, you see what's going on. And these kinds of infrastructures, manufacturing plants have often been misused in a software analogy, in the sense that this thing produces lots of the same things, cars of a certain make and model, and in software we don't even have that problem, right? If you want to duplicate your program 5 million times, you just burn another CD, so that the equivalent would be the CD pressing plant. And I understand it's even CDs are obviously out, so even every download from a web server is, if you will, a manufacture of an instance. So that's bullshit, right? But totally valid analogy is the following. In fact, um, no two cars within months built on such a uh, infrastructure here, I still forget the word, um, are the same. There's a huge variability. So in fact, these robots and these, infrastructures to build these cars are automated, mostly automated ways of handling variability, right? They implement, they know how to build cars, that's your subject matter, and then they are implementing a way of flexibly manufacturing almost like unique configurations instances of that domain of cars. So what you do here is you distinguish very carefully between the commonalities that every car has in common. Often these things are called platforms, right? You automate the variability within the domain of whatever Mercedes E-Class. Um, you tool up, right? You build tools, you build these robots, all these automated manufacturing things which are controlled by some backend that knows about which car needs to be assembled with which features. You hire toolsmiths, right? I'm sure that Mercedes in their production plants, and I only say Mercedes because I until recently lived in Stuttgart, so they probably have more robot programmers and machine configurators than they have automotive experts in the production, not in the design, right? And maybe that's wrong, but they have lots of these people. You invest in tool making machines, right? You go to the meta level, you build infrastructure to build these manufacturing lines. That's the word, by the way. And you understand production logistics, right? In software development, we do this up to a point. We build technical frameworks. We have built package, test, deploy, CI servers. There we automate, right? But we don't do it for subject matter. And I think that's a mistake. And I spent the last whatever hour explaining why. So one last thought on subject matter. I pointed out that we completely separate the subject matter from the technical stuff. And question is this really a qualitative difference compared to normal but well-structured code where you use, I don't know, POJOs, for example, to represent subject matter and keep it away from your whatever cloud infrastructure. So what do you want if you want to change the modeling technology, right? Aren't you just removing, or aren't you just moving the legacy problem one step further, in the sense that now you have to somehow disentangle your modeled subject matter from whatever language modeling tool that you decided, whatever, MPS or Langium? And the answer is, it is a significant difference, because you're not implementing your subject matter in this modeling infrastructure. You're describing it in a way that you understand. By you, I mean your tools. The semantics is well defined. You can always transform that, your subject matter, into some other representation that is now suitable for your new tool of the month, right? The Dutch tax agency, who are using that approach to describe tax calculations and public benefits calculations. They have traditionally done this with their own proprietary tool, and at some point they decided we don't want to evolve that tool anymore. We want to use MPS for that, and they automatically migrated all of their tax and public benefit descriptions, formal descriptions, models, programs, whatever, into the new world, and they ran, right? It's obviously always a bunch of details to consider, but luckily they also had unit tests, and so they could be kind of reasonably sure that the technical transformation of the modeling technology kept all the semantics of the actual subject matter models the same. So again, you can, because you understand the semantics of everything, and there is no technical stuff mixed into the subject matter, you can always transform it into whatever other form you need, or from. I built a cool demo. You can find it under the link down here, where I use, hey, I mentioned AI, where you use ChatGPT to automatically construct instances of your configurations. In this case, it was a demo about psychological evaluation forms from prose descriptions, right? Because your models are free of technology, it's not a lot of work, and maybe spend a week to build the infrastructure to let these models be created by AI. And again, I'm not suggesting AI can replace the whole thing, right? You don't need any models anymore. You don't need any formal descriptions. AI will solve everything. Hype, 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 cheers. Not my point, but AI can play a nice role. For example, if you don't really know how to get started with this modeling language that you use to quote program your systems, then you just describe a bunch of things you need and let the AI create an example model, and you look at it, you understand it, you modify it, you test it, you play around with it as a means of getting to know the language. So again, these insurance products, telecom pricing policies, tax calculations, salary calculations, tachograph rules, clinical drug trials, and digital therapeutics that I mentioned before, of course, surprise, surprise, have all been implemented with these kinds of programmability-oriented systems. I was involved in all of these projects. There's obviously many more projects I have not been involved in, including large-scale printer architecture, systems engineering, the electronics computer architecture for cars, municipality management system in Luxembourg, and then again the previously mentioned public benefits and tax specifications done by the Dutch tax agency. If you want to learn more, I didn't include links to my own work and to some of the other systems I know, because I consciously don't want to sell my own stuff here. But if you Google for domain-specific languages and MPS and model-driven software development or engineering or metadata or data-driven systems, configurable systems, platforms, these are kind of the terms you want to use when you start your research. And obviously you can ping me and I can give you some pointers as well. So, bunch of takeaways and another nice picture. Don't be put off by this whole terminology around languages and meta model and shit. Things have come a long way since your compiler course at university, right? Tools have become better. Just don't be afraid. It's sad that so many people seem to be turned off by this stuff. It's a mistake. Be on the lookout for domains where this kind of SME programming makes sense. I gave you a bunch of criteria, and the approach can be a significant boost. In some of the papers on my website, I have numbers, that I can cite from customers. So it's not a silver bullet, right? It's nothing is free, but it is a significant improvement to how you build systems. Familiarize yourself with some of the tools I mentioned, right? Again, having these code generation, interpretation, language specification tools in your toolbox as a developer is a great addition. Not too many people are good with these, so it's also a good way of distinguishing yourself from all the other competitors on the developer market. And even if you don't build, systems where, quote, all the subject matter is done with languages, even building your own little utilities sometimes as developers for developers is great tools. And then, of course, read the How to Understand Almost Anything book. It's, in my opinion, okay, I'm biased, but it contains lots of good ideas on how to do any kind of requirement engineering, of course, with a focus on understanding the domain for building a language. But even if you just want to understand the domain for regular development, like, for example, DDD, I think has useful stuff in it. And finally, this stuff is a lot of fun and satisfying, this way of working. So really take a look and maybe start your own system development with this kind of approach. All right, so this brings me to the end of the talk. This is where I usually ask if people have questions. Obviously, this is pre-recorded, so I don't know. But if you have questions, send me an email at felter@gmail.com, VOELTER@gmail.com. Ciao.